So we all know that position in relation to time is velocity, and velocity in relation to time is acceleration. But what is position in relation to position? Or momentum in relation to time? Or field in relation to velocity? Or this inverted triangle right here? All of those derivatives, what do they mean? Well, that's what we'll answer in this video, a video about the intuition for derivatives. And yes, in the last two videos of the short series I have covered both derivatives and partial derivatives, but that was from a more mathematical perspective. This time we'll tackle them as a physical tool, to build up an intuition for them, to make it easier for us in the future to work with them in physics. So, where should we begin? How about we begin with something we all know, that is, the simplest example of a derivative, velocity. So basically, a derivative of position in relation to time, or as we like to understand it, how quickly the position is changing in relation to time. So it's a measure of, after taking a certain step in time, how much our position changes, meaning that if our derivative is higher, it would move more. If our derivative is smaller, it would move less. That much is simple. But let's complicate it a bit by, instead of talking about position, taking our entire derivative and plopping it on there. This right here would give us a derivative of velocity in relation to time. So let's think about what this would mean this time. The answer is, this time we're checking how much velocity is changing over time, which means that if we have our cube traveling forward with some kind of velocity, this is telling us how much that velocity is changing over time. So acceleration, meaning high acceleration or low acceleration, no acceleration, deceleration. There we go. Now, I know that the examples I'm giving you are trivial and everyone here knows what velocity and acceleration are, but the point isn't to learn what they are, only to unlearn what they are. I don't want you to understand these derivatives because you remember what they are. I want you to figure out what they are based on the derivatives alone. And in order to show you what I mean, let's tackle a derivative that's really similar to acceleration, and that is momentum in relation to time. So, what is momentum in relation to time? Now, I don't want you to look up what it is. I don't want you to solve for what it is. What I would like you to do, however, is try to figure out what it is based on just this derivative. Okay, I'll give you a second. And here we go. Basically, if we have our cube, this cube has some kind of momentum. Now, after a certain amount of time passes, this momentum can change. And this derivative tells us how much it changes. It's really similar to acceleration, but with one crucial difference. If you have two blocks, one light, one heavy, if their velocities change like so, their acceleration isn't equal, but their momentum in relation to time is equal. Why is that? Well, it's because the same change in velocity would be a lot more difficult for the heavy block rather than the light one. Because that same change in velocity, due to the mass, means a much higher change in momentum. Or in other words, you need a lot more of something in order to change that momentum. And what is that something? Well, force. You need a lot more force in order to move the heavy cube harder. And that's why momentum in relation to time is a force. I really hope you can see it, because now is when things are really going to ramp up, by taking something like momentum in relation to position. Oh, isn't that a doozy? Well, I'll let you have a second to think about what it means, and have you got it? Well, if you tried looking it up, you probably had tough luck. If you tried thinking about it in terms of units, you probably got mass per time, which, once again, quite nonsensical. So why is it so difficult to come up with what this value would be? Well, that's because I just made it up on the spot. Yes, this is a completely made up quantity, which is why you can't think of it in terms of values that exist. Instead, think about it in terms of change of what to what. So, if we change the position ever so slightly, how much is our momentum changing? Right here, position represented with position, and momentum represented with arrows. Where would this kind of quantity be useful? Well, for example, imagine a snowball rolling down a hill. In that scenario, as it's rolling, it's picking up not only speed, but also mass. Or in other words, it's not only accelerating, but it's also picking up even more momentum. In that scenario, we can figure out by how much it's picking up the momentum by taking this derivative. There we go. Isn't that something? Also, a bit of a fun note on the side, if you do actually want to go with the previous methods of the units, then you can see that if we go back to our snowball example, it actually does make some sense, because right here we can vary the position of the snowball and then we can see how much mass it has picked up. So the units aren't quite as nonsensical as they would seem. I'm certain that this approach of actually taking the units in order to figure out where we should go with our calculations will not actually be ever repeated in physics, and this is not a foreshadowing. Anyway, let's get back to the point at hand. If you understand what this means, then congratulations. In my opinion, that means you've weathered the storm, and you should be ready to understand all sorts of wackiness. For example, derivative of position in relation to position. What would that be? Well, derivative of something to itself is obviously 1, so that would be quite silly. So instead, let's pick position in one direction in relation to another direction. What would this derivative mean then? Well, for the sake of making it interesting, let's say that these coordinates are actually normalized to the direction of our object, which is a fancy way of saying that the forward always faces forward. Okay, in that scenario, what would be the derivative of forward position in relation to sideways position? Once again, I'll give you the second to think about it on your own. Okay, second over. Let's think about it this way. If we move a little bit to the right, how much do we move? Forward. Well, doesn't matter. Moving to the right doesn't affect moving forward at all. Yes, I have tricked you, it's been a trick question. The answer is that this derivative is actually quite nonsensical, because one doesn't depend on the other, which means the derivative we get is actually 0. But what if? What if we have some kind of constraints on our system? What if our movement is restricted? What if there is a certain path that our object has to move along? A path which acts as a constraint? Well, if we want to move to the right, that means our path has to be curved. So in order for the derivative to be low, our object has to turn a lot. And in order for it to be high, our object has to go almost straight. Or in other words, this derivative is an inverse of curvature. Yes, I did an inverse of curvature because curvature is something you could have been familiar with, but I just wanted to make a point that the values don't exactly have to make classical sense. They don't have to be something you're used to on a daily basis. You can take a derivative of basically anything to basically anything else. And to that, you may say something like make it. That's idiotic. Why would a derivative like that ever be useful? And to that I say, I don't know. No clue, right? But that's not the point. The point is that in this video, I wanted you to develop an intuition which will be crucial in the future videos. That's because whilst things like derivative of position to time, velocity to time, momentum to time are all intuitive, in the future, with the Lagrangian formalism and Hamiltonian formalism coming soon in the next harmonic oscillator videos, we'll be talking about the Lagrangian in relation to position, Lagrangian in relation to velocity, Hamiltonian in relation to position, Hamiltonian in relation to momentum. This sort of thing will be a lot more common in more advanced formalisms. And so I hope that you understand it now. But just in case you don't, we're going to go over one more kind of derivative. Something special to end the video with. It does look a little bit more scary, but don't worry, it's actually quite simple at its core. It's just that the notation looks pretty terrifying, and there's also linear algebra chucked in there to make things even more difficult, but enough tiptoeing around the elephant in the room. It's time to talk about the del. So, the del. The inverted triangle. What is that operator? Well, let's first start with a little bit of context. What is an operator in general? Well, operator is kind of like a function, but whereas if a function takes in a variable and gives you another variable, like so, an operator takes a function and gives you another function, like this. And I feel like this is easiest explained with an example. So an example of an operator would be a derivative. If you take a derivative of f of x, what you get is f prime of x. You get another function. That's what an operator is. And so del is an operator, which means it will take some kind of function and give us another function. But that is del on its own. Del can actually be used in 3 different ways. It can be used like this, it can be used with a dot product, and it can be used with a cross product. And here is where we will require a tiny little bit of linear algebra knowledge, something that I haven't actually covered in the Bras and Kids video, and well, I will eventually cover, but for now we're going to just do a quick reminder. You don't have to think about it too much. We have vector spaces. R2 means that we have some kind of space made up of two numbers effectively. So this would basically translate to a vector of two numbers like x and y, like this. In this scenario, we are dealing specifically with R3, so having three numbers. The reason why is because our space is three-dimensional, and that's what we basically would like to describe. And we're going to have two different functions that we care about. We're going to have lowercase f, we're going to have capital F. What's the difference between them? Lowercase f will take in R3 and will map it onto R, whilst uppercase f will take in R3 and will map it onto R3. What this basically means is that the lowercase f will get a three-dimensional vector, and in return it will give us a single number, whilst uppercase f will take in a three-dimensional vector and will give us back a three-dimensional vector. Where would that be useful? Well, that's a really good question. For example, if you have some kind of field that only needs to be described with a magnitude, you can just use the lowercase f. So if you have some kind of field that tells you the magnitude of charge, for example, then you would take in the physical position in our universe, plug into the function, and what you would get back is that kind of magnitude, for example. Another example could be potential energy. That's a good one, where you have a function, into it you would plug in your position, and what you would get back is the potential energy. So that's a single value. You plug in a three-dimensional vector of your position, what you get back is just a single value that describes the value you're interested in. Capital F is a bit different in this scenario because that is R3 to R3, which means we give it a vector of position, and it returns a three-dimensional vector. This one is also particularly useful when talking about fields. When talking about fields in physics that themselves are vector fields. So basically we give it the position in our universe, and what it returns is a field value at that point, but for a field that points somewhere, which when it comes to electricity is useful, because when it comes to electricity, fields do actually point somewhere at any point. So if we have some kind of particle, the field over there is pointing, it has a certain direction basically that we're interested in, hence why capital F. I really hope that's clear enough, because that's actually all we need in order to understand these. First of all, we have the del, then we have the dot product del, then we have the cross product del. Dot product and cross product are just two different kinds of multiplication in linear algebra. In the Bras and Kids video, this would be basically a dot product, this would be a cross product. That's basically how this works. If you are confused by this, and I would really suggest you just watch that video, it will make sense then. So let's see what these all would be equal to, starting with del f on its own. Well, del f on its own is equal to basically a sum of three things. So here you can see it on the screen. I will note it down ever so slightly differently in order to save space, because there's absolutely no need for us to go into all of that. So basically it's partial of the function in relation to some kind of coordinate times ex. What is this ex? This ex is a basis. So where it is pointing. We can have, in our three-dimensional universe, you can imagine basically three different arrows, all pointing a different way. There's a 90-degree angle between them. I'm drawing something three-dimensional on a two-dimensional piece of paper. This would be a better visualization, and basically each of these directions would be the basis. So what we are talking about here specifically, it's basically giving us just like a kind of combined three-dimensional derivative. An easy way to see that would be just note down the definition of del on its own, which would effectively just be basically a vector of derivatives. Noting down sideways because it is quite a lot, but when we have our three dimensions, that would effectively just be like this, a three-dimensional derivative effectively. First derivative, second, third. It looks terrifying, but genuinely is that simple. What isn't quite as simple is why we get a dot product or a cross product. Well, the reason why we get a dot product or a cross product is because right here our result is also a vector, and you can't just multiply a vector by a vector using a good old-fashioned product. You need to use the fancy one. So let's note down what a dot product would mean. In this scenario, I noted it down ever slightly differently. This is abuse of notation, but it doesn't matter because I'm just trying to convey the basic idea. In this scenario, we have the same part as we had previously. This is the part that defines the del actually, but we are using the dot product to multiply it together with the f, the big function. And I could talk about this some more, but considering how I haven't given you the background of linear algebra, that will just confuse you for no reason, so don't worry about it too much, because the point is that all we effectively get at the end is just a sum of the derivatives in 3 directions. And very crucially, what we get is obviously in relation to the 3 coordinates, but we get the output of the function in that direction, in relation to itself. Okay? So we get how the function is changing in x direction, plus the y direction, plus the z direction. However, very crucial point, this is not a vector. This is not a vector, this is a single value. This is just a sum of all of them combined together. So, what does this value mean? And allow me to rephrase it for you just to make this a tad more understandable. What we're doing here is when we take the del dot some kind of 3-dimensional function, a function that basically gives us a vector field, so it points somewhere at any point in space. If we take the del of that function, what we get is its derivative in x direction in relation to how it rises in x direction, y direction in relation to y direction, and z direction in relation to z direction. So what does this mean? If you are a fair bit confused, you probably couldn't come up with an answer, but if you aren't, the answer was clear. It gives you the total change, the magnitude of change, if you will. Which means that if you have some kind of field, you are right here, let's say for example, and the field is changing a lot, like so, then this value would be high, because the derivative is going upwards really high, or down really high. It's going somewhere really, really quickly, which means that this del dot f would be high. It's that simple, it's a singular value. It is really tricky because when it comes to the del, the notation makes it seem terrifying. But in reality, both a del on the function and a del dot per function are deceptively simple. This one just gives you basically the magnitude of change. This one effectively just gives you change in 3 dimensions. The problem is that the cross product actually is difficult and confusing. That one is actually a bit tricky to understand. So with all of these, if you think you've got them, that means you've got them. They really are that simple. With this one, well, we'll have to pause for a second. Due to the nature of the cross product, I'm going to, well, I can note this down again if you'd like, because once again, what we're doing here is we are just taking a cross of the del operator with the function. But what this results in the end is obviously not obvious partial of f, and right here I'm just going to note down 1, which means f of x, for example, in relation to y, or sorry, f of z in relation to y. In this scenario, conventions do actually matter. And then f y in relation to z, all of that ex. That is confusing, isn't it? That is confusing, because basically this partial y, what it means is slight change in the y direction, like so. Partial z means slight change in the z direction, like so. Partial fz tells you, once you move on the z direction, how much the function is changing in turn. So let's say that I've gone a little bit up. What this would tell us is basically how much the z component of the electric field, for example, would have changed. Then this f of y tells me the same thing, but this time on the y direction. And in the end, we're multiplying it by a basis vector of ex, which is also a bit confusing, but what basically means that right here what we'll get is a scalar, so a single value, but in the end we're going to represent it as a vector where it will represent this direction right here, So my goodness, what does that mean? That's really confusing and horrible. And I mean, yeah, it is. It's combination of calculus and linear algebra. Obviously, it's always going to be horrible. But it's even worse because it's also curvature. How is this curvature? Well, okay, think about it this way. Imagine that you have some kind of vector field. For example, a field, a function of wind. How is that going to work? Well, that's simple. You will have some kind of universe, right? Universe you live in, which just happens to have wind everywhere. Don't think about it too much. Now, you pick a point in that universe, like this one right here. Now you'd like to know what the wind at that point is. So you take your capital F, into it you plug in the coordinates of your point, x, y, z, and what you get in return is the direction of the wind, x, y, z. So it tells you how much the wind, how strong is the wind in that direction, how strong the wind is in that direction, how strong the wind is in that direction. That's basically it. That's what this function is. But now let's say that you take the del cross that function. Oh, what happens now? Well, let's think about it. What does this derivative tell us? This derivative tells us once we take a step in the y direction, how much the z direction is changing. And for the sake of convenience, I'm going to flip is that x will be pointing upwards. Now you'll see y in a second. But basically what this derivative right here tells us is once we take a step on the y-axis, like so, how much is the z-axis changing? Like this. Maybe a bit hard to see, I might zoom in. So this is our derivative. It tells you if you're going in this direction, how much is this direction changing? Okay, that's simple. What does this derivative tell us? Well, this derivative on the right tells us once you move a little bit upwards this time, how much is the y direction changing? Like so. It is very reminiscent of the derivative of position to position we've been talking about a bit. But one crucial difference, right here we're subtracting the two of them together, which means it is slightly different. So why are we subtracting the two of them together? Well, it's because, if you think about it, let's imagine... Okay, we've been experiencing a bit of technical difficulties. Nothing unusual, I can take it again from the top. Let's ask ourselves a question. When would this value be high? When would it be high? Well, it would be high if this right here is high, or if this is low, because we're subtracting it. So when would this value be high? That's a good question. This value would be high when a little step to the left means a big increase by going up, which means in a scenario basically like this. The only difference between these two arrows is that the left one is moving more up. So this derivative would be high. Now, when would this derivative be low? Well, this derivative would be low when moving upwards, like so, results in smaller difference on the y, which means like this, arrows going even more this way. Okay, when would our total derivative be low? Well, in order to see when it will be low, we can just using the same exact logic extended the other way if we would like. Right here the arrow would be way flatter, right here it would not only be way flatter but smaller on the z, right here it would go even crazier, and then using the same logic it will be this, it will be this. It is a bit hard to see, it may not be exactly readable, but what this is showing us is the curvature in a way. If the value is high, then we're going quickly, we're curving away quickly. If the value is low, we're just not, we're going straight. And that's actually what this is a measure of. This is a measure of curl. This is a measure of just how much something is curving. And crucially, at the end, the reason why we multiply it by the component of our derivative is because that's how we just happen to describe rotation. If you have some kind of rotation, the axis of that rotation would not actually happen on this plane, it would happen perpendicular to that plane, like so, which means we need to multiply it by the only axis we haven't used. this is z to y minus y to z, and we're using the x-axis to describe it, which means what we would actually get out of this operator right here would be a three-dimensional vector describing the rotation, the curl, in every single direction. That's what we would get from this right here. And if you don't understand it, yeah, don't worry, that's fine. This is meant to be an extra example at the end to make sure that if you understood everything beforehand, you can create like an ultra depth understanding. But if you don't, then don't worry, okay? This is a combination of calculus, this is a combination of linear algebra, and this is a combination of rotations, which are absolutely bloody terrible. So don't beat yourself up over it, it is really annoying to understand. However, if you have managed to go through this entire video understanding all of the confusing topics, if you have actually managed to understand the del chapter right here, and if you would like some more, then what I would suggest is looking at Maxwell's equations and trying to interpret them. Because Maxwell's equations are a brilliant, absolutely brilliant example of using the del operator with the cross and the dot like so. So there we go. That will be it. I really hope this chapter wasn't too bad, and I really hope you've enjoyed this third video about derivatives. The reason why the third video is needed is because the next one will be about the Lagrangian harmonic oscillator, and it will require some pretty interesting derivatives that, well, before this video would probably not make that much sense unless you have specifically encountered these kinds of derivatives in the past. So I really hope you will be looking forward to it. If you would like to learn more, then I would really suggest the website. That's because this is all a part of a charity event that we have organized, and there is a website with more resources, links to all of the related videos, links to the papers written by Remco and Ash, and so I hope this helps you at least a little bit. For now, that'll be it. Thank you everyone so much for watching, and have a great day. Bye!